Thank you, Andrew. As Andrew said, my name is Chris MacLeod, and I, for the first part of my academic career, was involved in AI research. Um, in fact, my PhD is in AI, in artificial neural networks, which we'll be talking about a little bit today. And I'd like to say the talk is sort of split into two parts, really. Or there's two themes in it. One is about the development of AI from a sort of sociological and cultural point of view, to show you a little bit about what Andrew mentioned in terms of fear factor and where that's come from. And just to show you that AI is not something new. AI is actually something very old, and this is not also the first time that AI has had a large presence and everybody knows about it and everybody's talking about it. Far from it. That has happened several times in the past as well. And the second theme within the talk is just to give you an idea about the modern AI. You'll have noticed a big difference in what you can do with ChatGPT and Gemini and all these AI systems, and what has brought about that change. Why has this sort of happened quite quickly and suddenly, to try and give you sort of an idea of that and what the technology behind it is. So there's sort of two themes going on here. The historical one also gives you a bit of context as to why what's happened with the resurgence of AI at the moment, puts it into some sort of historical context. So hopefully, this is the second talk I've given, but the technology has improved drastically since the first one. So hopefully I'll be able to work all this. So let me start off with a bit of a sort of historical context here. The very first person we know about who talked about artificial intelligence goes right back to the Greek philosophers. Aristotle, in his writings and what we know about him that was reported by other people, discussed artificial life forms, artificial intelligence. And it even comes across in Greek myth. There are stories of heroes and men making artificial intelligence, if you like, and these play a role right back at that early time, 300 years or so before the time of Christ. So this was a very early, people were thinking about these themes at a very early stage, actually. And if you think right back to even things in medieval times, like the Golem of Prague and things like that, that involves artificial artificial life forms and all that sort of stuff. One thing I should explain is that there are many different forms of AI. And we're going to be focusing on the one here, which has led to the current interest in AI and ChatGPT and all these interesting applications. But it's only one of many different forms of AI. And the others are sitting in the background at the moment, but perhaps they'll have their day in the spotlight at some point as well. And the one, well, I'll explain shortly what the one is, which is currently around. If we go to just the early modern period in France, these are actually three automatons. Automatons were early robots made by this chap here, Jacques de Vaucanson. He was a French courtesan who built these models, and the most famous of them actually is a duck. The duck could waddle about, greet people, eat seed, go around, lay eggs, and poop out the seed that it had eaten. Even in these early times. There was a lot more science in early times than people realize. You probably will have heard of things like the Antikythera mechanism that was discovered on a Greek shipwreck, things like that. That was a clockwork computer which could calculate the positions of all the heavenly bodies to help people forecast eclipses and all sorts of stuff like that, and when to worship their gods. Until that was discovered, nobody had really got a clue that the ancient Greeks could be anywhere near as sophisticated as this. And we completely lost the ability, or we don't understand how this guy produced what he produced. But here's the interesting thing. When he did, it frightened people. And people were saying, well, men have become like gods now. They can create life. Look at this artificial duck. It's almost like a real duck. And the flute player could play tunes on the flute, and the drummer could drum. They were also early clockwork robots, really. And that spurred on fear, particularly among people who were scared that this automation might destroy their jobs. And so you had a rebellion against this, automatons and automation. Probably the best known ones were the Luddites, who destroyed textile making machinery in the first part of the 19th century because they were scared of the automation. They thought that their jobs would be taken away, and so they broke up the various pieces of textile machinery that were becoming more and more automated. An interesting thing about the Luddites is there actually wasn't anyone called Lud. He was a mythical character which was made up, and no one has ever been able to trace a real person. But they said, well, we follow Ned Ludd. That's the person we're following. It's his philosophy, but he never actually existed. But you'll see a theme coming up here, time and time again. Now, an interesting thing about looms is a lot of technology from looms went into computers in the same way as a lot of technology from wine pressing went into making the printing press. If you think about what a printing press is, a Gutenberg printing press, it's like a big wine press. You pull it, a plunger goes down, a big piston squashes the print onto the paper, and you can read it. Well, looms used punch cards. Anyone who's familiar with a Hartesley loom will know that there's ways of sort of programming it what to do. A lot of early looms used punch card mechanisms, and they were read by the machine so that you got the correct pattern of threads going across. And that went in, that is early computers used punch cards as well, and they are a direct descendant. So looms, in a way, were an early form of computer, or the technology was the same. And so what they're doing there, in a way, is sort of destroying the forerunner of the computer. So this fear is there right from the beginning.
They were right, weren't they?
Well, it depends. Depends. You can argue one way or the other, you know. The next sort of stage you come up against was this thing here, the analytical engine, made by Babbage in the 18th, well, not made, planned by Babbage. It wasn't, he didn't actually build it, but people at the Science Museum built that one. It's a model. This is famous because it's the world's first programmable computer, and it was purely mechanical. He suggested it, and he wrote programs for it and things like that. But this lady here, Ava Lovelace, wrote about it and wrote programs for it. She's sometimes called the first programmer, computer programmer. That's not quite accurate, actually. Babbage wrote programs for the analytical engine himself. Lovelace is an interesting character, though. She was a daughter of Byron, of Lord Byron. And Byron, being Byron, if you know anything about him, abandoned her when she was a baby and ran off to have lots of affairs with lots of different people in lots of different places in the world. But she was an exceptionally intelligent woman. Died quite young. But she is quite often quoted as the first programmer, She wrote programs for this thing, but she wrote extensively about artificial intelligence. She was the first person, you could say, of a more modern era after the Enlightenment who wrote about intelligent machines, wrote what they might be able to do in the future, and some of her predictions were very accurate, actually. So an interesting thing about women in computing is until the 1970s, most computer programmers were women. It was actually considered a female profession. And right from her time up until even the time of the Apollo moon landings in the 70s, most programmers were women, and practically the whole team that wrote the Apollo computer programs for landing on the moon were all women. It was only really in the sort of mid-70s onwards that men started becoming involved in this. So it was quite interesting. This is an example. This is a program she actually wrote to calculate binomial numbers. And she published this. And if you put it into the machine was never made. So she wrote this program for something theoretical that had never been done. It would actually work. And it generates a binomial sequence of numbers. So she was a clever woman, and she was quite, she could see what was coming in the future and talked about AI a lot. And because she did, and because of these developments, you had another series of fear come up about this technology. You can sort of trace a direct line from this automation and this sort of stuff happening at the end of the 19th century to the early 20th century, and the fear of AI taking over again. And so we have a whole series of things at the beginning of the 20th century where people are scared of, normally it manifests itself as a robot. And the reason for that is that robots are a physical thing that you can be scared of. Whereas ChatGPT is not quite so frightening because you can just stamp on your phone and that's the end of ChatGPT, but it's more difficult to tackle a physical robot. But you can see the same thing. This fear emerges yet again, and it goes in waves. And that's what I mean by this is not a new phenomenon. AI is not a new phenomenon. People talking about it isn't new, and the fear it generates is absolutely not new. And if you've ever seen Metropolis, it is quite a scary film. Now, let me introduce you to the most important two characters in our story, Warren McCulloch and Walter Pitts. They were at the University of Chicago in the 1940s. I want to talk particularly, McCulloch was a professor at the university. Pitts was a really interesting character. Pitts was an eccentric genius, and as a teenager, he ran away from home, and he wanted to go to the University of Chicago and listen to the lectures, so he lived in a broom cupboard. When the cleaners went out, he would sneak back into the building. He had a sleeping bag, he slept in the broom cupboard, and McCulloch spotted him in the lectures. You can imagine like at a large university with a big lecture theatre with 500 people, there was this smelly individual at the back, smelling of disinfectant and brooms. But McCulloch noticed that he was asking really pertinent questions and discovered what was happening, that he wasn't a registered student or anything like that. What I would give to have eccentric geniuses wander into my lectures and listen and work with me, but it doesn't happen here very often. And took him under his wing. And so Pitts and McCulloch started working together. But Pitts was always unstable. And in fact, he committed suicide in the end. He came to a sort of rather sad end. He got more and more paranoid. He burnt all his last work, and he committed suicide at the end of the day. He was a very unstable person. Sometimes genius goes with that. And But they published a paper in 1943, and this paper is the beginning of our story. By the way, you might think that Pitts is the eccentric bearded one on the left. He isn't. That's actually McCulloch. Pitts, the genius, is the one on the right. McCulloch was the scruffy, bearded one. Pitts, despite his broom cupboard abode, was quite presented himself in a reasonably sort of professional way. What they did in 1943 was, well, what they were interested in was the brain. They were studying the brain. And they published a paper called, a catchy title, A Logical Calculus of the Ideas Immanent in Nervous Activity. And what it was they were studying the brain. Let me just go back a slide. And they were studying brain cells. This is a diagram of a brain cell. The picture on the left there is a micrograph, a photograph through a microscope of a brain cell. And the diagram on the right just shows the main parts of it. So you can see here, that's the cell body where all the main parts of the cell are, including the nucleus. That's the nucleus in the middle that has all your DNA in it. These things around the edge there, which look like branches, are called dendrites. And those of you with a classical education will know that dendrite means a branch in Greek. And coming from this is a long piece of cellular material that goes up there, which is actually what's going down there, called the axon. And this is a brain cell. The correct technical name for a brain cell is a neuron. Spelled sometimes with an E if you're British and without an E if you're American. And what happens is that these things, some of them are specialized for getting information from the outside world. So for example, the rods and cones in your retina in the back of your eye are neurons. Just specialized neurons. There's neurons in your ear, which are specialized for picking up vibrations. There's ones under your skin, which are specialized for touch and heat and pain. And they pass, they gather this information and they pass it down the axon, that long process coming out of the cell body. And that is what we would refer to as nerves. Those long axons are the nerves which you could dissect out of your out of a living creature of some kind. And these sensory neurons send a signal up through the axons into your central nervous system, into your brain and spinal cord. They're further processed there. And then once they've been processed, another specialist set of brain cells or neurons send them down to your muscles and your glands to help you do things. That set that transmits it out to your muscles are called motor neurons. And in fact, what happens in a lot of degenerative diseases, including motor neuron diseases, that the axons come under attack and decay, and that's what causes that particular ailment. So McCulloch and Pitts were looking at this, and they were saying to themselves, could we make a mathematical model of this? And their mathematical model of the brain cell was what they published here. And so they made an artificial brain cell, really, within, they suggested it in this paper. And it's just a mathematical model. The little stuff on the right, on the left there, these X1, X2, X3 are the inputs. So that's like the dendrites gathering out information from the outside world. The bit in the middle is a bit like the cell body. It processes the information. And then the output there is like the axon. It produces the information. And all a brain cell does is it takes in information from the outside world. And if it is stimulated enough, it passes that information on. It's like a relay, really. If it gets enough input from the outside world, it just passes a signal on. And it does this, if I just go back here, it does this by basically generating a little voltage in the cell body, and that voltage passes down the axon a little bit like a wire here to the end of the axon. The end of the axon is called a synapse, and these synapses pass it on to other cells using a chemical called a neurotransmitter. And you may have heard of those, and you probably will have heard of some neurotransmitters. Dopamine, serotonin, acetylcholine are all neurotransmitters that you might be familiar with or have heard of. But you might say, how does this produce the activity of the brain? Well, the answer is that you can vary the strength of this connection. So if neurons are important, they have a big influence on other cells. If they're less important, they have a smaller influence. And that is what they modeled here. They had these inputs, but in order to sort of simulate the influence that these inputs had, they weighted them. They assigned them a weight, saying how strong they were or how weak they were. So that was fine. Now, there's an interesting thing about all this was that MacCulloch and Pitts were not interested in computers, were not interested in AI, were not interested in anything like that. They were simply interested in producing a mathematical model of this that might be able to help medical people or help people interested in neurology and all this sort of stuff, and just basically be able to calculate what neurons were doing. However, in the 50s, this chap came along, Frank Rosenblatt, and he actually made in electronics, not in a computer, but with actual physical electronics, relays and valves and stuff like that, actually made MacCulloch and Pitts neuron. And what he discovered was that it could recognize patterns. And in actual fact, in this picture, he's got it set up. There's a camera there, and he's got it set up looking at the letter C. And he has discovered that it can recognize the letter C. And he could actually teach it to recognize all the different letters of the alphabet. Why is that important? Well, pattern recognition is one of the most important things of intelligence. If you are an animal, you want to recognize, and you see something over there, you need to recognize if it's food, something that's going to eat you, something you can mate with, whatever. Recognizing the pattern, recognizing what it is one of the most important things that you can do. And so Rosenblatt basically found that it can recognize patterns, and it can do this by setting the weights of these different inputs that are coming from the pattern so that it only responds to that particular pattern and no other ones. When he did this, this came as a huge shock to people in the 50s because they were like, oh, recognizing patterns is a key aspect of intelligence. It's really an important thing that animals do. What's going to happen? Well, what's going to happen is robots are obviously going to take over the world, and so is AI. You may recognize a theme here. So in the 50s and 60s, we had exactly the same thing as happened before with Ada Lovelace, with the Luddites going back. People were terrified that AI was going to take over the world. And so you had Robbie the robot from Forbidden Planet, Gort from the day the Earth stood still, and that robot there, which actually didn't have a name, from Lost in Space. And there was a theme in all these shows that the robots were there to help people, but if they go wrong, you better look out. And again, there was this theme of, oh, this is really scary. This is going to kill us all. However, it didn't last. And it didn't last because in 1969, a very, very famous scientist in AI called Marvin Minsky, who you may have heard the name of before, he was at MIT, published a book called Perceptrons. These early models of the brain that McCulloch and Pitts had developed were called perceptrons. That was the name given to them. We now call them neurons, neural networks. He published a paper, published a book actually, where he rubbished it. Minsky rubbished them, called perceptrons. And he pointed out one very important thing, that this neuron that these people were using could not even simulate a very simple logic function. A logic function, for those of you doing engineering here, which is called the exclusive OR function. Doesn't matter how you set up the weights in it, it couldn't become an exclusive OR gate. And because Minsky was a really important person, the whole field collapsed. Everybody listened to him. And during the 1970s, nobody did any work in it at all. And AI sort of died a death. It was like a sort of a wilderness as far as that was concerned. A couple of people continued working in it, but the whole field essentially went dead. Until in the early 1980s, several things all happened at once. The first of all, a group of people published this book called Parallel Distributed Processing. This is yet another name for the same thing as McCulloch and Pitts discovered. It's actually got lots of names. Neural networks, connectionism, parallel distributed processing, perceptrons. It's got all these names because lots of people were interested in studying it. Psychologists, medical people, engineers, scientists were all studying it, and they all called it different names. But this book was a sort of antithesis of the perceptrons book I mentioned earlier. It said, actually, no, this is not rubbish. Yeah, one neuron cannot simulate an exclusive OR gate, but 3 can, and there's 100 billion of them in your brain. So why are we even worried about this? But not only that, what they showed was that there was a way of training these large networks. And that method of teaching them to recognize things, of training them, as we now call it, is an algorithm called backpropagation, which right up until this day is still the most important algorithm in neural networks. These other chaps came along. Hopfield, you may recognize that name because this year he won the Nobel Prize for Physics. And he won it for this work. This year, the Nobel Prize for Physics was awarded for AI because of the recent advancements made, but Hopfield published his work in the 1980s. And he's lucky he's still alive. He's well into his 90s. But the secret of winning a Nobel Prize is to live long enough. Basically, it's so many decades after you do the work that you win it that you're lucky if you're still around. I'll tell you what Hopfield did in a second. This other chap I met once, he was really grumpy. His name is Kohonen, and he was a Finnish scientist. I don't think he's still with us anymore. I think he may have died a few years ago. But he was your typical taciturn Finn. You know, he sort of stood there, didn't say anything, and was just grumpy all night. These guys, Hopfield and Kohonen, produced other networks which were based on this. Also, what happened in early 1980s, 1982-3, was the release of the IBM PC, which brought small computing into the reach of everyone. Everyone could have a computer on their desk at that stage. All these factors came together and caused a massive resurgence of this type of AI in the late 80s, mid to late 80s. And this is what they produced. They took the little neurons that McCulloch and Pitts had proposed, these little processors, and they connected them together in a network. And not surprisingly, this is known as a neural network. And suddenly it could do lots of stuff that was above and beyond the simple stuff that the early ones could do. It could recognize much more complex patterns. What Hopfield in particular did, I'll tell you what each one of them did. Well, what this book did was give a way of training this, of teaching it, of setting all the weights All these connections have a weight as to how strong they are, and that's how the neuron functions. The book set the algorithm for the weights. Hopfield discovered that if you, this is not shown in this network, but if you have connections going backwards from the output to the input, going backwards, what we might call a feedback connection, then this can not only recognize patterns, it can remember them. It's got a memory. And so it can actually recall patterns. You can give it a corrupted pattern and it will recall a perfect one. And what Kohonen did, apart from being grumpy, was he discovered another different way of teaching it, where it could teach itself. And it could even teach itself patterns that you didn't know existed. So it could look at data and go, here's a pattern that I didn't even know existed. So this all exploded onto the scene, and as per usual, mass panic with AI. Okay, you may be recognizing a cyclical theme here. This directly resulted in the Terminator and lots of other I can't say that, end of the world scenarios where robots came along and destroyed everything. But there was always a group sort of going on the good side. Oh yeah, but we can do good things with this as well. And you'll recognize that theme in the modern AI stuff as well. So there was always the disastrous theme and the sort of wonderful theme in it. But you'll see this cropping up again in the 1980s. Huge resurgence in AI, huge panic, and also loads of people going, oh, this is really good, we can do this, that. We won't have to do our laundry anymore or clean dustbins or all that sort of stuff. You notice again, though, there's another theme here, which I suppose is a bit less prevalent at the moment, which is it's got to do with robots. Again, the robot's like the personification of the AI. The robot's like the thing, the physical thing, which is standing up that's dangerous, which is a little bit lacking in the current one. So that brings us to now. And so there was a steady development of this technology. Then you'll recognize maybe this guy's name, Geoffrey Hinton. He was also a Nobel Prize winner this year for AI. When I did my PhD in AI, he wrote one of the most boring textbooks on it you've ever read in your life. And I used to give it to students I didn't like as a sort of punishment, tell them to read it. These guys, plus a few others, I've just really picked these three up as an example, in 2009 published a series of papers. And these papers are what have caused the current upsurge in AI. And what they suggested was actually really fairly straightforward. What they suggested was making this neural network bigger. Now, that seems like really obvious. By bigger, what I mean is sort of deeper. You'll notice that it's got layers. Okay, there's the inputs from the outside world, and then there's other neurons processing that, and other neurons processing that, and then there's finally an output that tells you what the pattern is. What they suggested is putting in more layers. The layers in the middle, you can see there, are called hidden layers because they're hidden from the input and hidden from the output. And they suggested make this deeper and it'll be able to do lots more stuff. Now, you might say to yourself, why did it take like decades to just think of that? And there were two big reasons. The first is that you can actually prove mathematical that a network that's got three layers, and this has three layers because the input's not considered a layer, 1, 2, 3, can do any mathematical function that you want, is capable of doing anything that you want. So why expand it to more layers? If you can prove that mathematically, and there's two different theorems that prove it, there's no need to go above 3. So nobody bothered trying, actually, to go above 3 layers in networks. And the second reason was that the algorithm which is used for training it, which you might remember was called the backpropagation algorithm, is not very good for bigger networks. So if you go into networks that are many layers, the algorithm doesn't work as well. But these three guys, or among others, decided to go beyond that, to expand the network up into many layers. And if you make it more layers, you make it deeper, and hence the term deep learning or deep neural networks. That is where that comes from, and you will hear that being mentioned all the time, deep learning. It actually literally refers to more layers within the system. And so you can make a deep neural network exactly the same as a slim neural network or a shallow neural network, but just with more layers in it. And what they discovered is that the early layers pre-process the information more. And because they pre-process the information, the network is capable of recognizing much more complex patterns. And to give you an example of this, the shallow neural network will recognize a face, but only if the face is framed exactly as it should be in the frame. In fact, they'll recognize a face better than a human being will. But a deep network will recognize the face anywhere in the frame. And the reason it can do that is that the early layers back here recognize circles here. And they go, okay, there's two circles in this. And there's this sort of sloping thing here. And there's this horizontal line here. So they recognize like the features of the image, of a pattern. And then the later networks put all these features together. Say, okay, if you've got two circles and you've got something go down there and you've got something going across there, that's a face. And so by putting more layers in the network, you allow it to process the image at a more elemental level, first of all, and then put that together. And that's exactly what our brain does. In the back of our eye, in the retina, there are cells which recognize horizontal lines, vertical lines, diagonal lines, circles, all these primitive features. And then as we go deeper into the brain, more and more layers of cells put these things together into more and more complex images. And the name of that theory that I just said is called the grandmother cell theory, because the theory goes that as you go deeper into the brain, we go from simple lines to more complex things to faces, but eventually you reach a cell which recognizes your grandmother as it builds up the information that's been presented to it a bit and a bit. And that's exactly what the deep neural network is doing. It's putting this together from primitive features and this was just a consequence of adding more layers onto the system. And so this leads us to what has caused the current revolution in neural networks. And the answer is three things. These deep neural networks, the fact that there's much more data available on the internet, so you can use the entire internet to train this thing to recognize what you want it to do. You can pick up all this information from the internet. And so rather than in the old days where you had to take pictures of lots of students and feed it into your network until it learned to recognize them all, you can now train the thing on the entire internet. And some technical innovations, the main one being the training algorithms for these large, deep networks, which did need a bit of innovation to get them to work. So they developed, in fact, the algorithms which are still used are variants of the backpropagation algorithm, but they've just been tweaked so that they work with these deep networks. Do these things have anything like intelligence? No, I think from the way I've just explained the way they work to you, obviously not. That they do not come to their reasoning through anything that's even remotely like human intelligence. They come to it through being able to recognize patterns extremely well, better than we can, because we can be fooled by all sorts of shadows and other stuff that's going on. These things are very focused. They're trained on massive data sets that are stolen from the internet, basically. So can they create something new? No, but they can combine things in novel ways. They can't learn anything that's not on the internet. The weights are set by the things they see, but what they can do is they can combine things from different people, different examples in different ways to produce novel mixtures, but not something that's truly new in the same way as a human might think of something completely off to the side. Does that mean that you shouldn't be scared of AI? No, it doesn't mean that at all. It just means you shouldn't be scared of this AI. That's not to say that you can't replicate much more complex neural networks in the future, which can do intelligent things and make decisions and be very dangerous. It's just that these aren't them. That type of network that I'm talking about is more likely to come out of a combination of neural networks and something called an evolutionary algorithm, which is an algorithm which mimics the process of evolution and allows you to evolve networks in the same way as an animal might evolve to become very complex. And that's incidentally what I did my PhD on, evolutionary neural networks. So these are very interesting. They're very sophisticated. They show up humans because neural networks recognize patterns better than humans do, that they always have. It's just that we can now train them on so much more data that they look much more sophisticated. Can they replace people? Yes, they can in certain aspects, particularly things that require circumscribed data. Bizarrely, I would say that if I was a doctor, I would be looking over my shoulder right now, a medical doctor, because that is definitely something that this sort of data can deal with, because it's a very circumscribed field where you're recognizing patterns, and the patterns correspond to diseases. And that's definitely something that they would be very good at. But now, somebody said earlier when we were talking about the Luddites, were they right or are they right? Well, right throughout history, we've had the same thing. Automation comes along, makes people redundant or makes jobs redundant, like the weavers and the Luddites. Every time so far, these people have been replaced by the people making the more sophisticated equipment. It's just that the jobs change. So rather than be the person whose job is replaced by the neural network, you might be the person training a neural network. It still requires somebody to do it. And these tend to be self-regulating systems. If you make lots of people redundant, then there's no money in the economy to buy the technology that you're developing. So the economy automatically sort of collapses itself. In the case of the Luddites, if you made all the weavers redundant, then nobody would have any money to buy the textiles that you're making in the first place. However, that's not what happened. What happened is that more people went into the design offices that made the interesting textiles and into other areas that involved supporting the new machines. At the moment, that's what's likely to happen here. But just because it happened dozens of times in the past doesn't mean that the pattern will repeat itself forever. So is there reason to be afraid of AI? Yes, in the future, but not with these current developments that are happening at the moment. They are not intelligent in any meaningful sense. They're just very clever. And you can certainly use them as a useful tool. Will they make some people redundant? Yeah, probably. But actually, maybe not the people you think. It is more likely to be people with specialist knowledge that are recognizing patterns, like medical people, I would hazard a guess at. So there we go. Any questions from the floor, providing they're easy ones? Is that the last slide, actually, Ali? Yeah. So that's an overview, hopefully a historical one, to show you that this is not the first time this has happened. This is an ongoing pattern that repeats itself cyclically over time. And if I had included the fear of automation in general and not just computing, you'd have seen even more bumps where people have got scared and worried and stuff like that. Nobody likes change. That's not a pleasant thing to go through, especially if you're perhaps one of the older people whose job has depended on things being working in a certain way. Okay, any questions?